For a moment, I'd like you to hold still and allow the scale of where you are to settle around you. Not the room, not the planet, but the larger architecture that contains them both. A thin atmosphere wrapped over rock, a small star holding a handful of worlds, a galaxy of hundreds of billions of stars, and beyond that, a sea so wide that even our finest maps become soft at the edges. If you'd like, watch this in full screen and stay with it to the end. Not because anything sudden will happen, but because some ideas only reveal their meaning when we give them time. Because there is a possibility, supported by a persistent thread of observation, that we are not simply located somewhere within the universe's grand pattern. We may be inside something, vast, invisible in any ordinary sense, and yet capable of changing what we think we see. It would not feel like an enclosure. There are no walls, no boundary you could point to in the night sky. But in the distribution of galaxies, in the subtle drift of light across distance, and in the quiet disagreements between our most careful measurements, there is a suggestion that our cosmic neighborhood is unusually empty. This is the idea behind what astronomers have come to call the KBC void, sometimes described as a local underdensity, a region extending out for hundreds of megaparsecs, where the number of galaxies and the amount of matter they trace appear lower than the cosmic average. It is not an absolute absence, it is a thinning. And in a universe where gravity responds to even slight imbalances over enormous distances, a thinning can have consequences. The first hints came not from grand philosophical debate, but from counting, the kind of work that seems almost too modest for cosmology. Tallying galaxies, measuring their brightness, assembling catalogs that try to be complete, and then asking whether our region looks typical. When those counts are sorted by distance, a curious pattern emerges. Close by, the luminous matter traced by galaxies appears deficient, then gradually rises toward a more ordinary level farther out. In one influential analysis, astronomers measured the near-infrared luminosity density of galaxies, using it as a proxy for the underlying distribution of matter, and found evidence for an underdense region on the scale of roughly 300 megaparsecs in radius, reaching toward the cosmic mean only at still larger distances. The work was careful, rooted in wide sky catalogs, and it gave this proposed structure its name: Keenan, Barger, and Cowie. As the KBC void entered discussion, other surveys and wavelengths added their own impressions. Underdensities had been suggested before in various forms, but what made this one remarkable was its combination of size and depth. In the language cosmologists use to compare regions, the density contrast is sometimes expressed as a deficit relative to the mean. In one formulation appearing in later literature on the subject, the KBC void is described with an observed relative density contrast on the order of delta approximately 0.46 plus or minus 0.06 between about 40 and 300 megaparsecs around the local group. Numbers like these can seem abstract, but their meaning is simple. Imagine the universe as it would appear in an idealized average, galaxies and clusters distributed according to the statistical rules of the standard cosmological model. In that model, there are fluctuations, certainly. There are voids, filaments, walls, and dense knots. But the probability of finding a region so large and so underdense depends on how lumpy the universe is allowed to be on those scales. And here the unease begins. Because in the standard picture, calibrated by the cosmic microwave background and by the growth of structure over time, the expected variation in density across regions hundreds of megaparsecs wide is small. If the KBC void is truly as deep and extended as some measurements indicate, then it would not be merely an interesting feature of the cosmic web. It would be a rare one. Rarity in cosmology is often described in the language of statistics, in sigma levels, how far an observation lies from what a model expects, given its predicted variance. Some authors have argued that the KBC void, taken at face value, would represent a many sigma deviation from the expectations of the standard lambda CDM framework, making it difficult to regard as a routine fluctuation. In one discussion of the topic, it is described as inconsistent with lambda CDM expectations at about the 6 sigma level, depending on assumptions and profiles. Such statements should be handled with care. The measurement of large-scale density is delicate, vulnerable to selection effects, photometric limits, and the complicated ways galaxies trace mass. And the mapping from observed light to total matter is never perfect. There remains active debate about the void's exact depth, shape, and even its full extent. Yet, the persistence of the signal across methods has made it difficult to dismiss entirely. If we accept, even provisionally, that we occupy an underdense region on these scales, we must then face a second question. What does a void do? Gravity in everyday life feels like an attraction. It draws us downward. It binds the planets to the sun. But gravity is also geometry, responding to gradients in mass and energy. In a region where there is less matter than average, the gravitational pull inward is weaker. Over cosmic time, that imbalance matters. In the simplest terms, matter tends to flow away from emptiness and toward concentration. But the motion we observe is not a stream of particles through static space. It is the collective evolution of the cosmic fabric itself, expansion everywhere, modified locally by the uneven distribution of matter. In an underdense region, the decelerating influence of matter is reduced. The result is that, relative to denser environments, the local expansion can proceed more quickly. This is not an additional force. It is the same expansion of the universe, experienced within a different gravitational landscape. The outward motion associated with voids is described in the language of peculiar velocities, departures from the smooth Hubble flow. Every galaxy participates in the general expansion, but each also has its own motion relative to that expansion, pulled by nearby structures and pushed, in effect, by the lack of pull from underdensities. In and around a void, these peculiar velocities tend to point outward, away from the void's interior, toward its denser boundaries. Now we come to a tension at the heart of modern cosmology, one that has been discussed with increasing seriousness over the last decade, the Hubble tension. It begins with a seemingly straightforward task. Measure the expansion rate of the universe today, the Hubble constant, by using nearby objects whose distances we can determine directly, then compare those distances with their redshifts. This gives a local value of the expansion rate. Then, independently, infer what that expansion rate should be by using the early universe as recorded in the cosmic microwave background, together with the standard cosmological model that connects early conditions to the present. This gives a value anchored to the young universe. The two do not match. The local measurements tend to be higher. The early universe inference tends to be lower. The gap is not enormous, but it is persistent and statistically significant, and it has resisted many attempts to explain it through simple, systematic error. A local void offers a conservative kind of explanation, at least in spirit. If our region is underdense, then nearby galaxies may have additional outward peculiar velocities on top of the global expansion. If we interpret those velocities as pure expansion, we will infer a Hubble constant that is slightly too high. In a detailed discussion of void-based resolutions, one line of argument suggests that a void can induce an apparent enhancement in the local redshift distance relation, raising the locally inferred expansion rate relative to the true global value. In the same 2025 analysis that revisits the void scenario using direct distance tracers, Earlier work is summarized as arguing that the KBC void could cause the locally inferred rate to exceed the background by roughly 10%, depending on assumptions. And yet, this too remains contested. Some analyses conclude that the void required to fully reconcile the Hubble tension would need to be larger or shaped in ways that are difficult to accommodate within the standard model's expected fluctuations. Others suggest that while a void might reduce the tension, it may not erase it entirely. In the same 2025 work, when models are fitted to certain direct distance datasets, the preferred void size in that particular approach can come out much smaller than the few hundred megaparsec scale claimed by the original luminosity density evidence, highlighting the uncertainty that still surrounds the picture. This is the nature of the debate, not whether voids exist, but whether the specific void we may inhabit is deep and large enough to matter in precisely the way we need. To understand why this matters so much, we must widen our view from local geography to the universe's structure as a whole. On the largest scales, galaxies are not sprinkled randomly. They form a pattern known as the cosmic web, filaments and sheets of matter meeting at dense nodes where galaxy clusters gather, enclosing immense low-density regions. This web is not a metaphor. It is a measurable distribution predicted by simulations that begin with tiny primordial fluctuations and allow gravity to amplify them over billions of years. Voids are not anomalies within this framework. They are inevitable. Most of the universe's volume, in fact, is taken up by them. Matter collects into relatively narrow filaments and walls, leaving great expanses where galaxies are few. When we say the cosmos is structured, we do not mean it is full. We mean it is organized. And in that organization, emptiness dominates volume. The densest parts are visually dramatic, rich with galaxies, bright in surveys, but they occupy comparatively little space. The vast majority of the cosmic landscape is quiet, underlit, and thin. The KBC void, if it is real in the strongest sense proposed, would be an unusually large instance of this general phenomenon, spanning a region in which the Milky Way and its neighbors sit within an underdensity that extends for hundreds of megaparsecs. Crucially, the Milky Way is not thought to lie at the exact center. We are offset, embedded within the interior, but not symmetrically placed. That matters because an off-center observer inside a void will see anisotropies in the surrounding structure, different depths in different directions, different contributions to peculiar velocity, and subtle directional effects in measured expansion if not carefully accounted for. In such a setting, even the concept of the Hubble flow becomes complicated. The Hubble law is statistical, a relationship that emerges when one averages over sufficient volume. But inside a large inhomogeneity, the average depends on where the averaging begins and ends. This leads naturally to bulk flows, another quiet but important observational thread. On scales of tens to hundreds of megaparsecs, galaxies exhibit coherent motions relative to the cosmic microwave background frame. Our own local group moves at several hundred kilometers per second relative to that frame, as evidenced by the CMB dipole, and this motion is understood as the gravitational response to the nearby distribution of mass, including great structures and extended underdensities. Bulk flows are expected in the standard cosmological model. They arise from the same initial fluctuations that seeded the cosmic web, but their amplitude and scale contest the model's predictions. In some discussions of the void scenario, bulk flow measurements become part of the constraint. A void that is deep enough to shift the local expansion rate must also produce a certain velocity field, and that field must remain consistent with what we observe in galaxy motions. The 2025 analysis notes that preferred void models while able to address aspects of the Hubble tension in some fits, can disagree with certain recent bulk flow estimates, illustrating how tightly these ideas are coupled. Underneath all of this lies a principle so foundational that it is often left unstated: the cosmological principle, the assumption that the universe is homogeneous and isotropic when viewed on sufficiently large scales. It is not a claim that matter is evenly spread everywhere, but that beyond some scale, no location is special. Living inside a giant void does not automatically violate this principle, because the principle is statistical. Even in a homogeneous universe, some observers must find themselves in underdense regions. But it does raise an uncomfortable possibility. If our location is not typical, then our measurements may not straightforwardly represent the global values we think we are measuring. The discomfort is philosophical, but it is also practical. Cosmology depends on the translation of observed light into inferred geometry and history. If local structure introduces a bias, then tensions between different measurements may partly reflect a mismatch between local and global reality, rather than a failure of physical law. Here, the KBC void becomes more than a map feature. It becomes a lens. Not a gravitational lens in the usual sense, but a lens of context, a condition that shapes the interpretation of what we see simply by being the place from which we see it. Where might such a void come from? In the mainstream picture, it begins with inflation, an early epoch in which quantum fluctuations were stretched to astronomical scales, seeding slight variations in density. Over time, gravity amplified these variations. Denser regions grew denser, drawing in matter and forming filaments and clusters. Underdense regions emptied further, as matter flowed outward toward the growing structures around them. In this sense, voids are not holes carved out later. They are the natural valleys of a landscape whose hills became galaxies and clusters. Their emptiness is a record of the universe's growth. And because dark energy now dominates the expansion of the universe, voids enter a new regime. In earlier epochs, matter's gravity slowed expansion everywhere, with local variations depending on density. But as the universe expanded and matter diluted, dark energy became comparatively more influential. In underdense regions, where matter is even scarcer, the relative dominance of dark energy arrives sooner and more strongly. The consequence is that voids can expand faster than denser regions, not because dark energy behaves differently there, but because there is less matter to counteract the acceleration. This does not mean voids are propelled outward by a mysterious pressure. It means that the balance of influences is different. Less matter, less deceleration, and so the accelerated expansion driven by dark energy asserts itself with fewer obstacles. Over vast time, the effect is cumulative. Voids grow, filaments stretch, the web becomes more tenuous. The universe, already dominated by emptiness, becomes emptier still. There is a future implied by this geometry. As dark energy continues to drive accelerated expansion, regions of the cosmic web will recede from one another faster and faster. Distant galaxies will slip beyond horizons where their light can ever reach us. The observable universe will shrink in practical terms, not because the cosmos becomes smaller, but because connectivity is lost. If we already reside within a large underdensity, that isolation may arrive in a slightly altered way. The local landscape shapes the rate at which structures around us thin out, the pattern of peculiar velocities, and the distances at which the universe becomes smooth enough to serve as a reliable backdrop for measurement. Over the far future, the densest nearby structures will remain gravitationally bound. Our local group and its immediate neighborhood will persist as an island. But the broader cosmos, especially across and beyond the surrounding void, will fade into observational irrelevance, not abruptly, inevitably. And this brings us to the quietest implication of all. A civilization that develops within a void inherits a biased view of the universe. Its sky contains fewer nearby galaxies to map. Its local measurements of expansion may be slightly elevated compared with the global value. Its inferred cosmic age, derived from those measurements, might lean younger, depending on the assumptions built into its models. Its sense of what is typical may be shaped by an environment that is, by definition, atypical. This is not a dramatic revelation. It is the kind of bias nature produces without intention, an observational selection effect written into our location. Even now, our most precise cosmological inferences rely on stitching together observations from different epochs and different distances, while assuming that the same underlying expansion history applies uniformly and that deviations average away. If we are embedded in a significant underdensity, that stitching becomes more delicate. The discrepancies we debate may not all be telling us about new physics. Some may be telling us about geography. The evidence suggests, at minimum, that the local universe is not perfectly representative on the scales that our most sensitive measurements probe. Whether the KBC void is as deep and extended as some analyses propose remains unresolved and continues to be debated. But the broader lesson is secure. The cosmos is structured, and structure matters when we use the universe as its own measuring instrument. In the end, the KBC void does not threaten cosmology so much as it humbles it. It reminds us that we do not observe the universe from nowhere. We observe it from a particular place at a particular time within a particular pattern of matter and emptiness. And even when we speak in the language of universal laws, our data are gathered locally, filtered through local conditions, and interpreted through models that assume we stand in an ordinary patch of the whole. Out beyond our galaxy, beyond our neighboring clusters, beyond the filaments that lace this region of space, there may be a vast, subtle dip in the cosmic density field, shaping the drift of galaxies and the slope of the Hubble diagram by a small but meaningful amount. Not a void you could ever see by looking up, but one you can infer by patient counting, by careful mapping, by noticing when independent measures of the same quantity do not quite agree. And as the camera of the mind pulls farther back, the Milky Way becomes a pale fleck on a filament. The filament, a thin thread on the edge of an emptier region. And that region, only one cell in a foam-like web that fills the observable universe. In such a view, certainty becomes difficult to justify. The universe remains what it has always been, vast, indifferent to our expectations, and perfectly capable of placing us in a location that subtly alters what we conclude about everything else. We may be inside a cosmic hollow, and if so, even our most careful measurements are, in part, a description of where we stand.